appreciate it, in particular the project of POEMA, because it brings together such different backgrounds and different skills, and I was really surprised when I read about the project, and I'm happy about that. Okay, this is mainly a survey type. Okay, so I tried to collect some things we did, or some people I know did, which is mainly based on polynomial approximation. So it's an approximation theory talk. I will try to give some ideas of some research topics and some heuristics we can try to grasp from some other theories. Okay, so the outline, okay, there is some propaganda first, of course. So I'm part of this group, the CAA group in Padua and Verona. This is a constructive approximation and application group. It is a small network of collaborations around the world. And okay, mainly the main guys are this Marco Ganello, Len Boss, Marco Cagliari, and Vincenzo Moriva, and Stefano De Macchi, which are either in Padua or in Verona. And we work, as I told you, on constructive approximations. What does this mean? Essentially, approximating functions, either with polynomials or by RBF functions, wavelets, whatever, both from the theoretical point of view, so rate of convergence, things like that, and from the algorithmic and numerical analysis point of view. So building robust algorithms and implement that on a computer. Okay, as I told you before, the idea of the talk is to give a brief survey on, well, say the part of our work which is most related to the subject of the workshop, and I have to say sorry. Maybe these slides are not so perfect, because when I've been here yesterday and the day before, I realized that my first try to prepare a presentation was completely wrong. It was not tailored on the audience, and so I typed this night, essentially. So, so if you find some typo, please don't tell me, but I was for sure. Okay, it was quite late in the night. Okay, we have also a workshop each year. Okay, sorry about this. This is the logo of some years ago, but I had no time to download the correct image this night. Sorry. Okay, the main topic is approximation theory, but depending on the year, we have quite different topics. So, group of people who decide to come to join us. The situation is kind of friendly and informal, and there could be also a very different topic which has some relation of some kind. Okay, each 5 years the workshop becomes a conference, which means it's larger, and there are quizzes. Okay, in the workshop there are just working groups, so people collect in small groups and attack problems. That's it. While the conference has also the talks. Okay, if you are interested, you can check the site. Okay, and attached to the conference there is also a journal. We managed to keep it free and online. And okay, this is again on approximation theory, but it's not a proceeding; it's really a journal. And this is DRNA, so Dormite's research notes on approximation. Okay, let's start with some background material. What does approximation people cares about? So what is okay? Well, posedness, stability, and convergence of interpolation schemes. So you start with a function with some finite dimensional linear space of functions, and you want to try to find the best approximation or approximation to the target function within this linear space, subspace. Okay, maybe some stability or, well, posedness first. Stability issues may appear, as usual, in the subject. and we analyze this kind of stuff. One possible tool to approximate is least squares projection, so L2 projection, simply, on some finite dimensional space. And okay, but usually I come from numerical analysis, and people in numerical analysis is much more happy when they have some kind of uniform convergence of approximations, not L2 or pointwise convergence of function, things like that, something more robust, like uniform. And so providing uniform convergence of sequence of approximation to a function is one major topic for us. Construction of exact quadrature rules with positive weights and 3 points. Positive weights is a very classical thing in quadrature. And why do we want positive weights? Because quadrature rules which has positive and negative weights are not stable from the numerical point of view. Okay, this is a, say, historical point of view. It's very old, and Gauss realized it first. But we will see that this has a direct application in polynomial optimization. Maybe in 40 slides we arrive at that. Okay. Well, two very relevant facts. First of all, I did not know anything about the relevance of polynomial optimization since few time ago. I didn't know that there are people working in such a subject, and even more important, so please excuse my ignorance, I didn't know anything about, well, I still do not know anything about algebra, and especially about the algebraic theorem. So probably I made some stupid questions during talks because I don't know anything about that. Okay, so what? Let's set up the standard setting for polynomial interpolation. So let's start with a compact set, which may be real or complex. But in any case, even if we deal with a real set, since we are working with algebraic functions, because polynomials are algebraic, it's better to look at such a set sitting inside the compact space. Okay? Maybe one-dimensional case or several-dimensional case. So small n will be the dimension of the ambient space. And I will denote by capital N the dimension of the polynomial space with the complex coefficients and with the n variables. Okay, so this is essentially, so we have this relation. Why I didn't close that, I don't know. So n is actually depending on the degree of polynomial, so small n, and the dimension of the space, and it looks like that. Okay. And at some point it will be relevant that the asymptotic behavior is like that. Okay. And we start with a continuous function, and since we are working with polynomial, it's not possible to, if K has no empty interior, it's not possible to approximate such a function by polynomials if you do not assume a priori that in the interior of K, the function is actually analytic. Okay? Oh, but maybe having some very bad behavior at the boundary, still being continuous. Okay, given an array of points of K, so this ball Z, which is nothing else but some points, and I take exactly the number of points corresponding to the dimension, I look for interpolation of such a function. What does this mean? Well, we look for existence of the polynomial in the space of polynomial of degree at most n. Okay, I'm using this notation, which might look very strange for people coming from algebra. This is quite common in approximation theory papers, so sorry about that. And you look for a polynomial which is interpolating the function at the nodes. So the values of the polynomial are the same as the value of the function at each node. And you ask for uniqueness of such a polynomial, and you try to compute it. Okay? So one possible way of attacking such a problem, which is a very elementary thing, is Lagrange interpolation. Okay? Usually in first year courses in math, you see Lagrange polynomials and I see some bored expression. I know this is very elementary. Okay, you usually define Lagrange interpolation in one-dimensional for one-dimensional problems. Okay, this looks quite different, but actually it's the same. You can find the basis of polynomials, generating all the space of polynomials of such a degree, well, less or equal to n, which are made by polynomial function, which are just one at a single node and vanishing on all the other nodes. And how can you provide such a basis? Well, you take the fundamental determinant. Okay, if you prefer, you can arrange monomials in maybe with the lexicographical ordering and compute the monomials at each point. You arrange that in the matrix, you compute the determinant, that's the usual fundamental determinant of the nodes and the polynomial space. And then you consider this ratio where you replace the ith entry by a variable in the upper part of the fraction and then not in the bottom. So essentially, of course, when red z is precisely zi, this is here 1. When red z is equal to some z j, which is not I, okay, this matrix here, the Vandermonde matrix, has a column which is repeated twice, so has 0 determinant. Okay, so and why this basis is such such important? Well, trivially, we can provide interpolation simply combining the Lagrange basis with the values of the function. Okay. So essentially, you compute the inverse of the interpolation matrix, and that's it. Okay, so at some point I have some easy sentence that I marked with the exercise for you because I didn't have enough either time or will to explain how it works. But it's easy, so I mark it with this red exercise for you just to get you not sleepy during my talk. Okay, okay, we can consider the linear operator I and both z, which is the interpolation operator, the linear operator acting on Banach spaces. Okay? So you endow the space of continuous function. Maybe I should write analytic in the interior if the interior is not empty. Okay, with this norm here. Okay, this is nothing but nothing more than the uniform norm over the Banach set. And you define this operator as we did in the slide before by interpolation. Okay, and you endow both spaces with uniform norm, and okay, you can look for the norm of this operator, the linear operator of Banach spaces, and you can verify that provided that the interpolation exists and is unique, which is something related only to k and to both z, you can compute the norm of such operator, and it's precisely the maximum of this stuff here, which is not a polynomial, not the sum of square, is something much more ugly, is the sum of modulus of polynomials, which is kind of ugly function. It's non-smooth, it's fast oscillating for big n, and it's just Lipschitz, nothing more than that. Okay, why is this norm important? Because we can bound the error of in uniform norm of the approximation of f by interpolation with the error of best approximation. So these are called in my background approximation numbers, or well, I should say uniform approximation numbers. So the error of the best approximation, sorry, this stuff is not, okay, It doesn't like you, but it doesn't like me neither. Okay. Sorry about that. Okay. This is the error of best approximation. Okay. We call it that approximation number. And this is quite easy to verify just because of linearity. The error of the approximation produced by interpolation is bounded above by the error of best approximation. This is depending on the function and on the set. Okay? Multiplied by, okay, I don't use the pointer, it's not the multiplied by what? By this norm of the uniform of the interpolation operator plus 1. Okay, this is an easy result. You can try to prove by yourself. I teach it in my first year course. And so you're splitting the error in two parts. One is depending on function and sets, the D and part, and the other one is depending on the how you set up your interpolation scheme. Okay, how you distribute the nodes. Okay, lambda n may be blowing up very quickly when n goes to infinity. That's what usually happens, unfortunately. And that's why interpolation may be not a very good tool for approximation sometimes. For instance, if you use what we call the standard interval, so -1, 1, or if you prefer the ball, the closed ball, unit ball in the one-dimensional real space, you can use equally spaced nodes. Okay, and say, okay, I want to approximate function. I want to approximate it everywhere at the same rate. Probably a good choice is to put equally spaced nodes. Maybe and heuristics that one can follow. Well, this is completely wrong. Okay, because the back constant, so the norm of the operator, which enters into that bound, I wrote the two lines above, grows in an exponential way with respect to the degree. Okay, so for instance, if your function is a quite nice function, can be approximated with polynomial uniformly on the interval with a decay of the error, which is a power of n. Okay, a negative power of n. Typically, this is granted by assuming that the function is k time differentiable, continuously differentiable on the interval. So the decay typically will be something like n to the power minus s. Minus k. It is k time differentiable. But in your bound, you're multiplying for something which is blowing up in an exponential way. So there is no convergence. Well, at least you are not. You do not know a bound which grants the convergence, and actually is what is happening most times.
So you have a sequence which attains the bound, the worst case bound, because it's just an upper bound. So
sometimes you can. Well, you need to change a little bit to make it easy. You can change a little bit the function to attain the bound for each n. Okay. But then you can also provide some function of the limit, which in such that the limit along n of this approximation number is going up. Of the bound is going up, and the fn is going to something, which is continuous.
Yeah.
Okay, another possible choice is Chebyshev nodes. I hope everybody heard about at least once in their lifetime. Essentially, you look at the interval. This is the projection of the unit circle on the real axis. You distribute nodes in an equal way on the circle, and then you project down on the interval. And that's Chebyshev nodes. Okay. Well, these are working way better because the back constant is growing approximately like the logarithm of n plus 1, which is way better. Okay. So it is sufficient that your approximation number are going to 0 faster than log, which is faster than 1 over log, which is not such a huge requirement. Probably Lipschitz is even more than what you need. Okay. Okay. So from approximation theory point of view, holding the growth of the back constant is a major thing because Otherwise, you can't provide it with the approximation by interpolation. In fact, unfortunately, it's practically unfeasible to try to attack the problem of optimizing the Lebesgue constant. First of all, you have an exponentially growing number of variables in the dimension. So you have a lot of variables. Okay, maybe one say, okay, maybe it's still doable. The problem is not sparse in any kind of sense. Okay, the function you want to optimize is non-smooth and non-convex, so it's very ugly. Actually, it fast oscillates, so maybe really from the mathematical research point of view, is an ugly function. And also at some point, at this point of generality, the constraint on the set K are quite general, so maybe to implement it is even worse than this.
So excuse me? So you are referring to an optimization problem in this slide?
Yeah, I mean...
what are the variables you're optimizing over?
Okay, so you can reach you have a set K. Oh, sorry. So you have a set K. Maybe it's an R2, okay? Fixed and degree, okay? So in this case, I need n plus 2 choose 2 points. Okay, so capital N is equal to n plus 2 over 2, which is more or less n squared. Okay. And then you look at each array of points. This is my Z1, Z2, Z capital N. Okay, and you move all these points. So you have capital N variables in R2, which are constrained in...
And you want to minimize the Lebesgue constant.
Yeah. There are people trying to do some numerics on this optimization problem, but so we consider maybe N equal 3, 4, that's it. And still is a, very hard problem from an optimization point of view. And the K is taken to be the simplex or the disk. That's it. No complex geometries, no varieties or something like that.
And if you would allow more points, since it's limited number, does it help?
So there's no more interpolation. You need to use discrete least square superposition. That's what I'm going to do, more or less. Okay. So one possible relaxation, if you want, of the problem is to look for candidate points. Okay. Well, oh, by the way, optimizer has a third Lagrange point. Okay. Because of the obvious fact. Unfortunately, this is a simplification of the problem, but it doesn't simplify it too much. So what one does, in place of optimizing the sum of Lagrange polynomials, so a sum of ratios, of modulus of ratios, one does, okay, what if I just optimize the denominator of the common denominator of all the fractions? So you take the absolute value of the common denominator, which is the modulus of the bundle on the term. And why one should be interested in doing that? Well, if you remember the expression of the Lagrange polynomial, which is this stuff in here, where I replace the z with some f, because now I'm talking about some particular choice which is factored in. Okay, so but they are nothing but points of k. Okay, you look at that, and if you chose the f guys to be the optimizer of the modulus of the bundle of the terminal, then this ratio, the ratio inside the modulus is at most 1. Okay? Because any other choice, put a w in place of fi, and well, this is another array of points, which is a competitor for the guys which are optimizer. So it's at most 1. And then you are summing up here, you're summing up capital N guys made of and each of those is at most 1. So you have automatically a bound for the Lebesgue constant of this array of points, which is precisely the dimension of the space. So this is extremely good because what is not optimal, we know that there are cases where the Lebesgue constant grows like the log of the degree. This is, sorry, the log of the dimension of the space. This is growing like the dimension of the space. So it's linear, not logarithmic, but is way, way better than the most of the points you can try to pick as, say, generically. And, okay, so for instance, this choice guarantees that if you start with the continuous function, which is an analytic in the interior of K, then the interpolation, the sequence of the interpolants to F, following any such kind of effective points, built on effective points, is uniformly converging to the original function F. So we are happy with this. Well, still not that much because we simplify the objective function, but still is a very ugly function because it's a modulus of a polynomial, and you still have a lot of variables, very general constraints. It's a very hard problem nevertheless. Okay, so another small and stupid exercise for you, just to get acquainted with these fact guys. Fact arrays are not in general unique, okay? And this is not only due to possible symmetries of a set. And you can try to compute the effective points of the set K, which is the boundary of the unit disk in C. Guess how they will look like. And there is a hint, you can try to use the Hadamard inequality for the derivatives. This picture here, okay, these pictures are about some approximate factors. So we have some numerics, which is capable of producing arrays of points. Here we have a polygon, and I'm looking for arrays which are behaving in a similar way to factor arrays, but they are not factor. Okay, it's just to give you a picture of how they do look like. So, for instance, okay, these are for different degrees: 10, 50, 20, 30, and 40. I don't know why my computer made this picture smaller. I don't know. Maybe it's too much points. I don't know. But as much as you go further with the degree, you should see, I don't know, on the back you can see that, but there is some clustering of points at the corners, especially on the corners which are pointing outside. Okay. While in this vertex here of the polygon where there is no convexity, and here you should see that there are some kind of missing points. So sorry.
No, conclude, but...
so one may wonder if this is a geometric fact, an analytic fact, or something else. I will try to give some understanding of this thing in the end of the talk. Please?
No, I don't understand where the complex unit circle is in the picture.
No, it's not in the picture. So, okay, sorry. The first part of the slide. So
the picture is not related to the exercise.
Exactly.
Okay.
So then there is a picture to make a picture.
Yeah.
To show that they are not. This is precisely they are approximate factor points. So K is this strange shape. Sorry. And in which sense are they approximate? Well, so for fact, I can try to do this. Okay, for faculty, you have the modulus of the Vandermonde of Z1 up to Zn, and you consider the Vandermonde with monomials up to degree n is equal to the maximum. Okay? And then one may wonder, okay, this quantity is probably blowing up as much as n increases to infinity. Is there any asymptotics of the maximum? The answer is yes, actually. And you need to raise this function to some exponent. And the correct exponent is 1 over capital N. Remember that this is depending on small n as well. Okay? So this has an asymptotics when computed at maximizer. Okay? And this quantity is very relevant to what follows. And the points in the picture are not attaining for any fixed n, the maximum, but the asymptotical value, I mean the limit. So I produce some kind of approximate technique. Okay, so the sequence of points is also depending on degree. Okay, and when I take the limit here, okay, I obtain here the same asymptotic as vector. Which, by the way, is called the transfinite diameter. We will see that. Okay. They are the same asymptotic as the maximum. They are almost maximizing.
And so for this picture, there are plenty of points. So it's easy to find maximizers of the this determinant?
An heuristic, but I will say something later. But we can simplify forward the problem. We can first try to find a discrete model of the set K. Well, actually a finite model, points. And then we optimize there. But we do not optimize the determinant. We compute a QR factorization of the rectangular matrix. Okay. And this is a Gaussian elimination with partial pivoting. And actually what happens is that you are extracting some rows of the matrix such that the determinant of a square matrix is the maximum one among each possible choices of rows.
Interesting.
Okay? And this is much more easy than try to optimize.
Yeah, maybe you get into it after, I don't know, but just for information to make connection with Monique's talk, the moment matrix, its Cholesky factor is this van der Waals matrix. Yeah. So if you want to access the determinant of the van der Waals matrix, you can also, up to some exponentiation, maximize the determinant of the moment matrix. And this is in statistics, it's known as the D-optimal experimental design. Maybe you'll talk about it.
Choose slides from the end. Okay. I will talk about that.
Good. Sorry to spoil the effect.
Because you call it a moment matrix, but I call it Gramian because it's a scalar product. There. Okay. Let's go on. And this is about approximation by interpolation. Another tool we may use is discrete L2 projection. So let's endow our set K with some probability measure. Okay? It may be supported on the whole set or may not. But the support is in K. And okay, we can consider the L2 of mu norm, which is nothing, okay, from bracket, everybody knows what is that. And it may happen that L2 of mu defines a norm on the space of polynomials of degree up to 1 or not. It depends on how looks the support of the method, actually. And in the case that it defines a norm, we can speak about orthogonal polynomials, well, orthonormal polynomials. So fixed ideas, you can arrange your your moment matrix, and you can try to run a Gram-Schmidt procedure, and you end up with some, well, actually this is the only way to define the orthonormal polynomial in a unique way, because if you start with some ordering, then you have the basis, which is order, okay? And that's orthonormal polynomial. Okay, the space of, if the L2 mu scalar product induce a norm, the space of polynomials up to degree n endowed with such a norm is a reproducing kernel Hilbert space. What does this mean? Well, it's a Hilbert space where the point evaluation of function, well, Hilbert space of functions, where the point evaluation is a continuous linear function. Okay. And when this happens, there exists a function, okay, such that f of z is equal to the scalar product in the Hilbert space, of course, of f and some function depending on the point. Okay? And this is called the reproducing kernel of the space. Basic function analysis. And since you have a finite dimensional space, this is actually quite trivial in this setting, and you can compute exactly the kernel, which I denote by this k and mu, depending on two variables, because, okay, one variable is here, and the other one is even here, is the variable where you realize the product. Okay, you can write it simply summing up the orthonormal polynomials multiplied by themselves, okay, in such a way where you take, if you're considering complex sets, you need to take conjugation because you don't know if the orthonormal polynomials are real polynomials or not. Okay, it's quite relevant to consider the so-called Derman function. Somebody calls it the, okay, one of my collaborators, we are always fighting about the name of this guy, this function. Because actually, the reciprocal of such a function is something extremely classical in approximation theory, which is Christoffel function. Okay? But I do not like to say, okay, let's consider the reciprocal of the Christoffel function, because it's quite lengthy. So I use this notation, this name, which is less customary, but is more compact. Okay, this is nothing than the diagonal of the kernel. So we consider the kernel when w is equal to z. Okay, so it's the sum of the square modulus of orthonormal polynomials. And you have this nice variational characterization of the Derman function. So this is precisely at each point the values of the value of this function is the maximum value of the square modulus of the polynomial, say in the space, divided by its L2 mu norm. Okay? So this is an easy exercise if you want to check this. But this is a useful thing in various exercises. Okay, so we can try to produce approximation to function by projection. Another very easy and fundamental thing. So we can set up this linear operator acting on continuous function. If k has non-empty interior, I must require that f is also holomorphic in the interior of k. And I can define the approximation of f as the best L2 approximation on the linear space of polynomials. This is just, you have an ambient space, which is maybe infinite dimensional. You pick a point, you have a linear subspace, and you compute the orthogonal projection. Okay, the best approximation is the orthogonal projection. This is termine di Pitagora, come si dice in inglese? Pythagorean theorem. Okay, nothing than that. Well, in infinite dimension is the same. Okay, so we have some estimate of the norm of the operator and on some bound on the error of uniform approximation by L2 projection. So if we go back one slide, you see that this function here is playing the role of comparability of norms. Take the supremum of this function on your complex set. This means that this value, which is numerical value, is the constant of constants. Sorry, my English is hard. Is the constant of norm comparability between L infinity and L2 mu norms on the space of polynomials. Okay? That's why if we endow this space with L2 norm and this space with L infinity, we got that the norm of the operator, this line here, is bounded above by the square root of the suprema of this Berman function on the set. The square root is due to the fact that, see, here we are considering square modulus divided by square norms. That's it, nothing more. Okay, and similarly to the back constant, we can bound the error of approximation by projection by 1 plus the square root of the third function. And here, P and star is nothing like the best approximation on F in uniform norm over K. Okay, so is this working? Well, we should be a little bit careful because it depends on you. Okay, we have plenty of freedom. Okay? We can move mu in an infinite dimensional space, actually. So, and we may ask under which possible additional constraint we have that the convergence of the approximation to F holds uniformly, maybe on K, maybe on a larger set, even, as the degree of the polynomial space you are considering tends to infinity. And then maybe once one will say, okay, there is some class of measure for which this procedure is well working, but maybe asymptotically or as rate of convergence, some measures are better than the other. And this is a huge topic, is Bernstein-Markov property. Also, we can consider a slightly variated problem for numerical problems. Okay. Of course, using a projection with respect to some very nice measure, maybe absolutely continuous with respect to the back, things like that, is attractive from the analysis point of view. But to implement that may be a little bit complicated in a computer, so we prefer finitely supported measures. Maybe these measures are just quadrature roots for a given measure, maybe not. Okay. So these mu n guys are just the sequence. So it's a slightly variated problem because in the first, in the slide before, the measure is fixed. Here is changing the degree, possibly converting to something. Okay? And still, I may ask, can I provide some conditions okay, for which this uniform convergence holds? Okay, these are the typical questions we are working on. Okay, these are quite elementary, probably. They're not so sophisticated. But still, we have, even improving this kind of stuff, there is some trouble.
So
what?
You are changing the measure with the degree of the polynomial that is interpolating. This code can be hiding some branch phenomena. Because if you change the measure, maybe the measure is changing how you measure the oscillations. And
yeah,
maybe it's hiding what is happening. If you change the measure.
No, you don't measure the error. Okay. The measure is used only to provide the approximation. Then you measure the error because you want to grasp such kind of phenomena like in uniform. So you don't want that some bad oscillation occurs when you have very nice approximation in the middle, like in Ruge, and then at the boundary you have big oscillation. Yeah. But you are measuring with uniform. So everything is going to zero uniformly or not. Okay. So this is the introduction of this modification of the problem is just because maybe I want to use quadratic points, which are not maybe exact. Maybe you want to use a quadratic rule which is approximated. Sometimes it happens. Okay, so this formulation includes also such kind of stuff. Okay, a possible approach to this kind of problems has been reformulated in a new approach, which is quite new, back new, in 2008, with this introducing this natural definition. And it will be, well, I understood why it's natural after years of studying such stuff, so I don't want to explain it here. But, okay, what's the rough idea? If we try to sample polynomials, not according to, for instance, the bag measure on nice compact set, but according to something which is designed on polynomials, on the polynomial behavior, maybe we can, and we need to sample in a lot of points, but not too much, essentially. Then we can combine some easy techniques to prove some charter bound on convergence of approximation. So let's make this definition. We consider a sequence AN, so at each degree, we consider a finite subset of the set K, like interpolation. Okay, before I had a compact set, a being-like set with some points. But here, I don't assume that the number of these points is according, well, it's the same as the dimension of the space of polynomial of set degree. Okay, it's just any number within space of points. Okay, I turn and I consider a sequence of this subset of the set K. Well, I assume two things. First of all, the cardinality of this set is growing at most polynomially with respect to the degree. Okay? So, for instance, interpolation nodes, which are growing like degree to the power dimension of the ambient space, are fine. But then I ask another thing. See, and another norm comparability requirement. I compare the uniform norm over the whole set K with the uniform norm just on points. Okay? And I call this number here, well, the worst case number, the supremum of all polynomial of degree at most n, less than the zero polynomial, of the normal, uniform norm over K divided by the uniform norm over AN. Okay? This number might grow very fast. My points are not catching the behavior of the polynomials. Okay? I call this number Cn, and I want that also this number here is growing, okay, but at most polynomial with respect to the degree. And there is a better case where actually this sequence of numbers is boundable by some constant C. So in the first case, I call this sequence of sets AN weakly admissible mesh, or polynomial, weakly admissible polynomial mesh. And one, if the sequence of constant Cn is boundable by some C, then I call this admissible. Okay? And some examples. If you consider Quadrature points, interpolation nodes of very nice bad constant in the unit interval, well, the cardinality is growing like the dimension of the space. So at degree n, you have n plus 1 point times n. Okay. For any n larger than 1, you can produce an admissible mesh with a fixed constant. Sorry for the typo, but in principle, you can have this C here, okay, this C here, to be 1 plus epsilon for any epsilon small as you want. For any fixed epsilon, you can find an n such that the Quadrature points of degree n times m of epsilon are an admissible mesh with such constant 1 plus epsilon. So almost have the maximum of polynomial of this discrete set of points, finite set. Okay, we work quite a bit in my group in building admissible meshes. Standard construction and also a lot of examples relies on classical polynomial inequalities, which are some tools comparing the derivative, usually the derivative of polynomials is boundable by some function times the norm of the polynomial. You can change norms, uniform, L2, your favorite norm, things like that. And maybe you can change also the derivative order. Okay? But there are plenty of such inequalities. The main one are due to Markov, Bernstein, Zigo, and some other mathematicians. Okay. So why are we interested in these admissible meshes? Well, if K is polynomial determining compact set, so if a polynomial is vanishing on the set, then it is the zero polynomial. And we pick any admissible mesh, we can look at projection, and we have this bound here on the error of approximation by B-square projection. So what does B-square projection mean? Well, to the mesh, we can associate a measure μn, as I told you before, which is simply the uniform probability measure of the mesh. but it's not a discretization of the uniform probability measure on the set K, like normalizing the Lebesgue constant, because the spatial distribution of points is usually very far from being uniform. Okay? And with this bound here, you can prove that for any continuous function on the set K, which is holomorphic in the interior, if the interior is not empty, can be uniformly approximated by polynomials, and you have convergence of this kind of approximation. Okay, some properties of these sets, they are not that ugly because they preserve some properties. For instance, any set having a Markov inequality, which is a fairly general requirement. So, for instance, any closure of a Lipschitz bounded domain has a Markov inequality. Possess an admissible mesh of cardinality. This, well, sorry about that, but D should be an M. I changed my notation in this slide, sorry. So the cardinality is growing depending on the dimension of the ambient space, and an exponent, which is one piece of the Markov inequality, which depends actually more or less on the geometry of the set. Okay, then you have some other properties, which are, for instance, they are stable like under linear isomorphism. So if you rotate, take any linear image, non-degenerate linear image of a set with an admissible mesh, and you take the image of the admissible mesh, okay, it's still an admissible mesh with the same constant. They are stable under unions, so you can switch your set split in parts where you can produce a mesh, can produce a mesh, can produce a mesh, then you take all the mesh together, and you have an admissible mesh. As I told you before, interpolation points with slowly increasing Lebesgue constants are ruled in such a sense. Maybe you take some more points, so you use at degree n, interpolation of points of degree n times n, for instance. Then they are mappable. Well, it follows by definition is more or less an exercise. If you have a polynomial mapping, okay, and phi j, which maps your set K or some set Q, and you know how to build a mesh, an admissible polynomial mesh for your set K, then you consider the image under the map phi j of the mesh at the degree n times j, and you take it as a mesh of degree n on the set of the image set. This is okay. It's difficult to tell it, but it's a fairly stupid statement. Very, very easy, because you want to have a set the map Tj, which goes from map precisely k on q, for instance, okay, and you have a polynomial here, polynomial p going on c, okay. So if the composition of these two polynomials has degree at most, what's the degree j times degree of p, okay. So if I sample the polynomial with a mesh which has here, I take the mesh a n times j. By definition, the norm of p on q is equal to the norm of p composition j on k, and by definition of an admissible mesh of degree n times j, this is bounded above by the constant of the mesh times p composition j on the mesh itself, and okay, this is equal to c times p uniform norm of the image of this. Okay, this is very easy. And okay, what else? Okay, you can also use Federico points. If you, by some knowledge given by God, are capable of computing exact Federico points, then you take degree n log n Federico points and you use it as a mesh at the stage n, and that's an admissible mesh. But this is not computationally feasible because you are not able to compute Federico. but still is interesting from the theoretical point of view. Okay, some other properties. You can also consider analytic mapping in place of polynomial mappings. Okay, so what happens in place of taking the degree here, in place of multiplying by the degree, you multiply by log n, and still this estimate is true. Well, not precisely by log n. And there exists a sequence of number which is growing like log n. Okay? And okay, as I told you before, answering the question, there are some linear algebra numerical algorithms that are capable to extract from an admissible mesh a sequence of arrays which is behaving like fact in the precise sense I told you before. Okay, we have a software package working on this construction of this set, computation, numeric, scientific computing based on admissible meshes. If you want to download the software, you can find it there. Well, it's not that efficient, but still working. Okay, as I told you, we can try to construct admissible meshes on a huge variety of different kind of sets. Usually, the construction relies on this kind of stuff. So, polynomial inequalities are a fundamental tool. Usually, we require or we use some sort of smoothness of the boundary. Okay? Possible symmetries in the set. Algebraicity of the boundary, they play a very nice role because usually you have polynomial inequalities on lower dimensional sets, like algebraic varieties or varieties, are very different in the analytic case and in the algebraic variety case. And this essentially is due to the fact that the dimension of, you can consider the polynomial space of degree n in the ambient space, you look at the variety, and the space becomes smaller, okay, and so the tangent derivatives of polynomial behave in a very specific way in the variety, and the kind of polynomial inequalities you can write to bound the tangent derivatives looks very different. And then you have polynomial mapping and unions. Okay? So the final aim is to build some weakly admissible or admissible mesh, and you want the cardinality to be as small as possible. First of all, for computational issue, but also there are some theoretical stuff. You use meshes, and usually you want the cardinality to be as small as you can. But remember that by definition, on an admissible mesh, you must have that this thing here. So E on the set K is less or equal to some constant positive. Okay, and from this exercise for you, prove that the cardinality of An is greater or equal to the dimension of the polynomial space you are considering. Now that is.
So maybe in 5 minutes you can conclude. I don't know how many slides you still have to cover, but it's time. But take some 5 minutes to.
Okay, maybe you're frightened by this number, but I
have
that's a lot of additional materials, maybe for questions or maybe for public discussion.
Good.
Sorry about that. I usually hide the number with a trick, but you know, at half in the
that made me nervous.
Don't care about this small stuff. Maybe you just hope that anybody's looking at that number. Okay, these are examples of admissible meshes of degree 15 for a U, which is the intersect of the difference of two circles, and this is a length, which is an intersection of the two circles, and a star, which is a star. The degrees considering here is 15, 15, and 25, and why they are different? Well, the same reason of the number there. I was looking for my bad, I wanted to go to it and I want to compute different degrees. I have old images in my computer. I could do that. Okay? And there are fundamental differences in this. Here we can see some sort of very neat behavior. There is some accumulation to the boundary and strong accumulation to the corners. Okay? The middle figure is the same, but the right figure is different because you have accumulation of points also in other regions. It's also interior regions. And why? Because this mesh has been constructed by combining all the techniques I told you about, including union. And union, there is some accumulation of points clustering in not really desirable places. Let me say it like that. And we can overcome that by some techniques, but it's more complicated. Okay, of course, a possible target is to hold the cardinality growth. Okay, you want a mesh which preserves such inequality, is more constant, possible, but you don't want to use 10 millions of points. This is another example with two meshes. One is very, very fine. Probably you see something gray, but there are points. There are some millions of points. And the other mesh is the blue one, which has been built by another technique. So one technique, you have some million of points. The other technique, you have some hundreds. And it's very different. Okay, this is not in the news, by the way. Okay, this, the smart one is using the fact that you have a smooth convex body, essentially. And so you can do a lot of geometric analysis, use balls, and use some final rest. Okay, so some application to polynomial optimization of this stuff. Of course, we can try to, well, we wrote some papers building these meshes. And then at some point we saw that we can use the meshes to optimize polynomial. So this, I would like to describe this approach as smart brute force, because you're making brute force on a smart set. Okay? So the possible question you may ask is, okay, there is some constant. The constant is small. Of course, it can't be smaller than 1, because otherwise you have stupidity on the blackboard. And can we let it to 1? So can we produce a mesh with very small constant, very close to 1? And why we ask this? Well, another easy exercise. If an is in the mismo mesh at degree n with constant 1 plus epsilon, and we consider a polynomial of degree of constant n, then the error on the minimum of the polynomial computed on the mesh, so smart brute force, and the true minimum is bounded above by the same epsilon times the range of the polynomial on the set A. And giving bounds with respect to the range is something very usual and customary in polynomial optimization. I learned. I know this good. Maybe I have 2 more. Okay. So the idea is to look more carefully to the construction we already did some years ago, in order to sharpen it and to bound the number of points, not only with respect to the degree, but also with respect to the dependence on epsilon. Okay? Because once we prove that we have constant 1 plus epsilon, then we have the bound. Okay, so we have some example of these applications. First of all, cubes. First set we would like to work on. We consider Chebyshev points. So this kind of set of points on the interval. Actually, they are called Chebyshev Lobato because they are also the extreme of the interval. Okay, and we take the Greek. So tensor multiplication of these points. And well, for any epsilon, there exists some k of epsilon such that this is an unmissable mesh at degree n of constant 1 plus epsilon. So for the result I told you before, the minimum is bounded above not only by the range, here there is some sharpening, by the maximum actually. Epsilon times the maximum. And we work a little bit on the how large is this k epsilon. There is some algorithm to compute that, and actually the cardinality of the grid is growing like n over the square root of epsilon raised to the power dimension of the space. Okay, so this is quite slowly increasing epsilon actually, not that much. I didn't expect that this would be sufficient. If you use equally spaced points, you will have in place of square root here, you will have square. So 4 order of difference. Quite smart. Okay, this is smart brute force. And then there are some other applications of the same kind. For instance, maybe there are too many S there. For convex volume, okay, we can sample this AN of epsilon can be explicitly constructed by some algorithm, and it looks like the blue mesh of the Cassini oval I showed you before. And still, we have a bound depending on the range of polynomial. And here we have this dependence on epsilon, which grows actually like epsilon to the minus n. Okay, so it's less better than in the cube. And why? Well, in the cube we exploit the fact of the tensor structure. Here we do not have, so we pay 1 order. Okay, one other construction, possible one, is to consider a star-shaped body. So we really use for polynomial policy the fact that it's star-shaped. So there is a point such that any line connecting this point to any point in the set lies inside the set, and you have some sort of regularity of the boundary. This regularity is C11, which is actually there is equivalent to the fact that on the boundary there is a ball which should be tangent. This is not, sorry. Okay, and the radius is uniformly chosen. Okay, and these two balls can roll on the boundary without entering or going outside of the set. This is C11 regularity of the boundary. And you can recover the same order of growth as in the tensor case, in the cube case. And this is quite general set. Okay? So if this is computable, there is some algorithm computing such a mesh, then you use smart brute force on that, and you compute the minimum of the polynomial up to such error, which will be very small. Okay, one maybe last thing, and then I will stop. I thought you present this thing about the minimum eigenvalue. Okay, so we saw the localizing matrix. Okay, we start with the set. This is not mine. It's curve result. Okay, we start with the set K, which is real now. Okay, so we have the set K, and there is a measure mu, which is precisely supported on K. Okay, the support of mu is equal to K. So the Lasserre hierarchy bound on polynomial optimization given by sum of squares can be rephrased, completely rewritten, as the problem of finding the minimal eigenvalue of this matrix here, where you consider, well, this is the function you're optimizing, so a polynomial function of degree R, and these are the orthogonal polynomials with respect to such a measure. Okay? So you can look for the minimal eigenvalue, and this is precisely the lower bound of the sum of squares of degree n, because here you are truncating the matrix up to degree n polynomials. Okay, we are happy, and the bound is converging to the true minimum of the polynomial. Okay, that's good. Very nice result. I like it so much. But okay, we can try to replace the measure mu with a quadrature rule. And what? So, in principle, you have points. You write an exact quadrature rule which has supports on points. Okay? And usually, we can provide that starting by an admissible mesh by linear algebra. Okay, but what happens? If you are able to to compute a quadrature rule which has positive weights, not a general quadrature rule. So it's about solving a underdetermined linear system with positive solution. We want positive weights. Well, what happens is that the minimum of the function is bounded above by the minimum function of the quadrature points, which is bounded above by the sum square bound. So everything is converging to the true minimum, and we have some algorithm to compute this. So one slide. Okay, I thought I could speak about these things, some complex PDE approach to approximation, but I have no time to discuss this. But in this setting, there is some reference method, which is, for instance, in the interval, is the usual Chebyshev method that people working in approximation uses a lot, because Chebyshev polynomial are so cool. There is the extension of this concept of the Chebyshev method to any other set in one-dimensional complex space, type logarithmic potential case. And we call such a measure equilibrium measure. Then there is a very, which is solving such a problem. But this concept may be extended with a...
Sorry.
We can eat while doing this.
Sorry, okay. This measure has a several dimensional counterpart. And, my guess is that... Sorry. Okay. This is the classical thing I wanted to show. Okay, with quadrature, you can try to optimize by the minimum eigenvalue. Okay, and usually you have some bounds that have been computed for some sort of measures. Okay, for instance, for the bag measure on a nice scale, or things like that. And there are some instances for which the sum square bound attained by the eigenvalue is converging faster than the other. And in each of that cases, the measure they used is precisely this equilibrium measure. So my guess is that actually this convergence here is a general fact and not a coincidence. Let's go to the last thing.
Okay, thanks. So for the sake of organization, we propose to move directly to the lunch place, and please direct your question to your speakers during the lunchtime. Thanks again.
You go eat here and you can explain.